In this lecture video, we continue talking about simple random sampling. Up to this point, our focus has been on how to analyze data from a simple random sample for the purpose of making an inference about the mean of a finite population. Now, obviously, that occurs after the data has been collected. But another point in time at which considering the method of sampling is important is at the planning stages of an experiment. And one aspect of planning an experiment that involves sampling a population is to determine the sample size required so that our hypothesis tests have a certain amount of power and or our estimators have a certain level of precision. And so that's what our focus is going to be in this lecture video: how to estimate a population mean with a specified margin of error, and in particular, determining the sample size that will result in that margin of error. So suppose that a simple random sample is to be selected from a finite population of size cap n, the population mean being mu and the variance sigma squared, and the purpose is to estimate the mean of the population. Now, in particular, we want to estimate the mean of the population with a certain margin of error. So the mean of the population is denoted by mu. It is unknown, and that is the object of our inference. We want to estimate mu to within a certain margin of error. The variance of that population is denoted sigma squared. And as usual, we will typically not know the value of sigma squared. In some situations, we may have an approximate value based, for example, on prior studies, but in many situations, we won't have any information at all about sigma squared, or we won't have reliable information that we would want to use. And so we may have to use some other approach to come up with an approximation for the population variance or standard deviation. So with that in mind, what is the sample size required to select from a population if we want to estimate the mean of that population with a margin of error of no more than a value that we'll denote by cap E? Well, the sample size required, the sample size needed to estimate the mean of the population such that the point estimator has an approximate 95% margin of error of E is given by this formula here. So the sample size required is little n is equal to 4 times the population size times the population variance divided by 4 times the population variance plus cap n minus 1 times the square of the desired margin of error. So the margin of error that we want shows up in this formula in the denominator in terms of its squared value. We also have showing up in the formula the population size and the population variance. Now, in order to use this formula, we would obviously need to know the population size. We will have, because we determine the desired margin of error that we want. But the problem is that this formula also involves the population variance, which we said that we probably won't know. And so what we'll have to do is either estimate it from a prior study or approximate it some other way. Now, to do that, what we can do is think about back to when we talked about Chebyshev's theorem and the empirical rule. And we may be able to use one of those rules in order to come up with a reasonable approximation for the population standard deviation. Now, once we do that, the sample size that we obtain from this formula will result in a margin of error that is at least approximately equal to the desired margin of error E. So let's look at an example of this. So the average amount of money for a company's accounts receivable must be estimated. No prior estimates of the population variance are available, but it is known that most accounts lie within a $100 range of the population mean, whatever that population mean happens to be. Suppose further that there are 1,000 open accounts. And so determine the sample size needed to estimate the population mean with a margin of error of no more than $3. So the population size here is 1,000. That's the number of open accounts. The desired margin of error is $3. And so we want to determine the sample size that will allow us to come up with a point estimator of the population mean that has a margin of error of no more than $3. And so the first thing we need to do is to come up with an appropriate approximation, a reasonable approximation to the population standard deviation. And to do that, we're going to utilize the empirical rule. You'll remember that the empirical rule said that if a population is unimodal and fairly symmetric, then approximately 95% of the values taken on by a random variable from that distribution lies within 2 standard deviations of the population mean, whatever that population mean happens to be. Now, an interval that is centered at the population mean and it goes 2 standard deviations on either side of that population mean, that interval has a width of 4 times the population standard deviation. Now we're going to take that and combine it with the statement that said that most of the accounts lie within $100 of the population mean, whatever that population mean happens to be. And so combining those 2 pieces of information, that would imply that 4 times the standard population standard deviation, which that's approximately equal to the range of values taken on by the accounts receivable values, and that range was approximated to be $100. And so then we can solve for the population standard deviation, and that would tell us that the population standard deviation ought to be about $25. So we can use that as a reasonable approximation to the population standard deviation. Once we have that, then our approximation for the population variance would be the square of that, or $625 squared. Again, the population size is 1,000. That's the number of open accounts. And so we want to find the sample size, lowercase n, so that the margin of error E, and again, that's the approximate 95% margin of error associated with our point estimate for the population mean, we want that margin of error to be approximately $3. Okay, so we plug these values into the sample size formula. All right, and so you can see here that we're plugging in 625 for or as an approximation to the population variance. We know the value of cap n, we know the value of capital E, which is the desired margin of error. And so when we go through the calculation, we get a value of 217.56. Now let me just point out, be careful and make sure that you do square the desired margin of error. That's a common mistake people make, all right? And so you have to be sure that you square that. And so we get a sample size of 217.56. Now, obviously, we can't have a fractional sample size, and so whenever we have a fractional sample size, what we're going to do is we're going to go to the next larger integer. Even if the fractional part, even if the decimal part is less than 0.5, for example, if this had been 217.25, we would still go up to the next larger integer, all right, and that should help ensure that the margin of error associated with our point estimate is no more than cap E. So that is how we use the formula, the sample size formula, to come up with the size of a simple random sample that will allow us to estimate the mean of a population with a margin of error of no more than a specified level. We do have to think about how to come up with reasonable approximations to the population variance. And one way to do it, as we've seen here, is to use the empirical rule, all right, which tells us that the range of values taken on in the population is roughly equal to 4 times the population standard deviation. Now, we could use Chebyshev's rule, but if we use the empirical rule, that's actually, I think, better, because that's going to give us a more conservative value for the population standard deviation, and therefore it should help us to ensure that the margin of error is no more than the desired level. So that's the end of this lecture video. We'll continue on in the next lecture video looking at inference procedures for a population total.